And we're going to move to chapter 7, which is the central limit theorem. In this lecture specifically, we're not covering the whole chapter. We're just going to cover the first 2 sections. But so without needless to say, let's just get into it. So the first is I'm just going to kind of intro it a little bit, just give you a few things to look at. And really what the central limit theorem does is it takes our normal distribution, and now we don't know, we know a couple things. We know that we have a sample size, has to be one of 2 things have to happen. Sample size has to be more than 30, or sorry, I should say at least 30, so 30 or more. And then it could also be, or it could be, we know it's normally distributed. So what the central limit theorem states is that if we collect samples that are large enough, the result will approximate a normal bell curve. So as we collect more and more and more and more samples, our distribution will start looking more and more like this bell curve. And what it means by large enough, again, is sample size that is 30 or more, or the data should come from a normal distribution. And there's 2 ways of doing this. This is where we're going to focus. This separates our two sections. There's 2 ways of doing this. One, we can calculate each sample's mean. So calculate each sample's mean. Or second, we can calculate the sum of each sample. All right, so as you can see, it's separated us into 2 sections. So the first section, we're going to look at the sample means. So we're 7.1, and it is the central limit theorem for sample means. We like to say it's averages. All right, so we're going to suppose that mu of x is the mean of x. All right. In the previous chapter, we just wrote mu. We just wrote the mean. We didn't write any subscripts unless we were trying to distinguish between maybe the first mean or the second mean or the first. Really wasn't sample mean. It was more the data values like x sub 1 or x sub 2. We also have now our sigma sub x, which is the standard deviation of x. And so I'm going to kind of say it again. So as the sample size, we're going to use n for our sample size. As sample size n increases, the random variable x bar, which consists of sample means, tends to be normally distributed and so we would say x bar normally distributed, and we're going to write mu sub x. Now, instead of just writing sigma sub x, because we're looking at the central limit theorem and we're talking about sample size now, we don't know quite if it is normally distributed. Okay, this is what we're approximating it to be. We have to take the standard deviation and divide it by the square root of our sample size. So kind of what I said previously, I'm just going to say it again, and you can write this down, is the central limit theorem for sample means says that if you keep drawing larger and larger and larger and larger samples and calculating their means, the sample means form their own normal distribution. So as we keep doing something over and over and over again, we're going to start approximating this bell curve, this normal distribution. That's what the central limit theorem states. So let's also talk about our z-score. Okay. So our z-score is now x bar, there is our random variable, minus our mu sub x divided by, instead of just sigma, we also divide by square root of our sample size. There's a couple things to add to this to know is that your mu sub x is the average of both x and x bar. Then I also want to let you know that sigma sub x divided by square root of n is the standard deviation of x bar and is called the standard error of the mean. So we're going to get right into an example. I think I'm going to have to go to another page. I don't think I'll have enough room. All right, so example 1. Oops. An unknown distribution has a mean of 90 and standard deviation of 15. We're going to say sample of size n equal 25. So sample size of 25 are drawn randomly from a population. So what this states is, as we keep growing these sample sizes, it's going to start forming a normal distribution. So A, find the probability that the sample mean is between 85 and 92. So our x bar is going to be the mean of a sample of size 25. Okay, so we're all testing this out. So first, we have our mu to be 90, right? It says it right here, mean of 90. Standard deviation now is next going to be 15. So our standard deviation is 15. And then our sample size is 25. So as we look at this, we have 90 And we know that we want it between 85 and 92. So 85 and 92. We want this in between. So first, let's find our z-scores, and then that we can find our probability. So let's say that this is our x1 here. It's going to be x2. Okay, so that means our first z-score is going to be x bar sub 1 minus mu sub x, standard deviation sub x, divided by the square root of n. Now we substitute our values. So we have 85 minus 90 divided by 15 divided by the square root of 25. And you want to try to put all of this in your calculator at the same time. All right, so for us, we can use a TI-30 in all the things that we do, or something equivalent to a TI-30. So I'm going to write here in this orangish, goldish color exactly what I would put into my calculator. So I first want my numerator. So in my numerator, you're going to put 85 minus 90. Then you're going to hit divide, and that's a slash when it types in your calculator. Put in another parenthesis because now this is going to be our denominator. And we have 15 divided by the square root button, and that's going to put a little square root with the parenthesis. You're going to put 25, and then end that parenthesis. This parenthesis here ends this one, and then you need one more. This one ends this one. And then you can hit enter. And when you do that, you will get negative 1.67. Okay, now what do we do with that negative 1.67? This is where we're going to use our table. All right, so we're going to go to our table. I'm not looking at negative because there's no negatives on this because it's about probability and the distance away it is from the mean. So it's all positive. But since we were negative 1.67, we're going to be looking for 1.67. So 1.6 is over here. And then now we look for the 0.07, which is right here. And so you can see that the number we're looking for is right here, the 0.4525. .4525. That's what we're going to be using. Now I have to find our second z value. And we're using our other data point, or data value. This one's 92, so 92 minus 90 divided by 15 divided by the square root of 25. And you're going to put exactly the same thing as you did here, except for instead of 85, it's just going to be 92. Right? So I can actually recopy this if I wanted to, so you can see. The same thing that you put in your calculator, almost identical. And then that equals 0.67. Again, it should be positive because it's to the right of the mean. So now what we're going to do, go to our z table here. So we're looking for 0.67. So 0.6 is right here. And then 0.6 and then 0.07 right here. So we're looking at this 2486, 0.2486. So now this 0.4525 is the probability right in here in this shaded region. And this 0.2486 is this shaded region right here. We want both. So what are we going to do to these two values? We're going to add them, right? So the probability, the probability of us getting between 85 and 92 is 0.4525 plus 0.2486. We calculate this and we get 0.7011. This is the probability. Or we could also say it's a 70.11% chance that the sample mean is going to be between 85 and 92. I'm going to have a part B to this. Part B says find the value that is 2 standard deviations above the expected value 90 of the sample mean. So first off, we got to start thinking about what this really entails. And really, I want to find the value. So the value is going to be my average, my mean, plus, because it says above, right? Above the expected value means we're going to be adding standard deviations to it. If we were below, we would be subtracting the standard deviations. The number of standard deviations times our standard error of the mean, which is sigma sum x divided by the square root of n. So right now we look like this. Value equal to our average, which was 90, plus we want to be 2 standard deviations. Remember, it's above, so that, remember, this above tells us that it's addition. If it was below, we would be subtracting. 2 times 15 divided by the square root of 25. You're going to put this into your calculator. I'll show you what you're going to put. You'll put 90 plus 2 parenthesis 15 divided by the square root of 25 and 2 parentheses. And this will give you 96. So 96 is the value that is exactly 2 standard deviations above the expected value, which is 90. Expected value is the mean of the sample mean. All right, let's move to our second and final example of the section. It says, in a recent study, reported October 29th, 2012 on the Flurry blog. The mean age of tablet users is 34 years. Suppose the standard deviation is 15 years. And we're going to take a sample size of n equal to 100. So A, what are the mean and standard deviation for the sample mean ages of tablet users? And this one might be like, I mean, didn't it say? It does, but working you through the problem. So it's asking for the mean, which again, it was discussed, it's 34 years. And the standard deviation, which is, what did it say, 15 divided by the square root of 100. So that gives us 1.5 years. So even though it says the standard deviation is 15 years, we want to know the standard deviation for the sample mean. That's when we have to divide by the square root of n. So that does change. So that gives us our starting point. So B now says, what does the distribution look like? What does the distribution look like? I'm not going to write the answer. I'm just going to tell you. So remember, the central theorem states that for large sample sizes n, the sampling distribution will be approximately normal. So isn't this considered a large sample size? Or we just the large sample size had to be 30 or more. So at least 30. This is definitely bigger than 30. This is 100. So based off the central limit theorem, and it has a large sampling size, this states that the distribution will be approximately normal. Okay, so C, find the probability that the sample mean age is more than 30 years. So find the probability that the sample mean age is more than 30 years. So let's draw this visually. So our mean was 34, and we're going to say more than 30. So it's going to be shaded everything to the right. So let's look for our Z value. Remember Z and our, our data value that we're looking for is 30. So 30 minus 34 divided by, we already had known our standard deviation. We found it up here. So we could just write 1.5 now that we've stepped into this. So 1.5, you should be able to put that to your calculator and you get negative 2.67. And we're not looking for negative because we're talking about the distance away from 0, the standard deviation. So 2.67. So 2.6 is what we're looking at. 2.6. And then 7. So go up to 0.7 right here. So here is our data point right there. 0.4962. Okay, so this 0.4962, remember this just means the probability in here. But we don't want just that. We want all of this. So if this is 0.4962, we also already know what all this is because this mean separates it in half. And to the right is 0.5 and to the left is 0.5. So the probability that X is bigger than 30 is we have 0.5 plus 0.4962. This gives us 0.9962. This is our solution to the probability that the sample mean age is more than 30 years old. So roughly 99.62% of the people are 30 or more. Or more than 30, sorry, more than 30. All right, last part. Find the 95th percentile for the sample mean age. So if we're looking at our distribution here, we know that this is 0.50. And then we need to go here. So to get to 95, we're looking for the 0.45. So if we look over here, we're looking for 0.45. And it looks like 0.45 as we keep going right in here. So we actually are going to use the smaller value instead of overshooting it. So we're going to use here, which is 1. I'll zoom out a little bit. It's 1.64. So 0.45 for us. The closest one was 0.4495. Or use 1.64. All right, so what that means, that's our z value. So our z value is 1.64. So x bar, our mean is still 34, and our standard deviation we know is 1.5. What we end up doing is we take 1.64, multiply it to 1.5, and then add 34. So it looks something like this. I'll put it in red here. So we're going to multiply it both sides by 1.5. Basically taking this and dividing this out here, that 1.5 on the other side. And by doing that, then on the left-hand side, we get 2.46 equal to x bar minus 34. Next, we add the 34 to both sides to get rid of it over there. And we end up with 36.46, which is our value. So this says that the 95th percentile for the sample mean age is 36.46 years old. Okay, so let's move to our next section here. The next section is 7.2, and is the it's the central limit theorem. So this time it's for sums. And I'm just going to go ahead and, I guess I can go ahead and write this first. We'll say this. We say that the sum of x is normally distributed. And we'll say n, so the sample size, times mu sub x. That's our mean now. And then we have the square root of n times sigma sub x. So the central limit theorem for sums says that if you keep drawing larger and larger samples and taking their sums, the sums will form their own normal distribution, and then it approaches a normal distribution as the sample size increases, just like we did previously. The normal distribution has a mean equal to the original mean multiplied by the sample size, which you see there, and a standard deviation equal to the original standard deviation multiplied by the square root of the sample size. So that's how we now write it. So we've been transforming this normal distribution and what is the mean and what is the standard deviation. So if these are the means and standard deviation, then to find the z-score, we have the summation of x minus our now mean. That's how you find your mean now. And then our standard deviation, which is square root of n times sigma sub x. And just have a couple of things I already said, but I'm gonna go and write it down just so you have it. Remember that this is the mean of the summation of x, or we would say the mean, and then we would have summation of x subscript. And likewise, the square root of n times sigma sub x is the standard deviation of the sum of x, or we'll write it like this. Notice how we're just adding the subscripts to mu and sigma. All right, let's move to our next example, which would be example 3 in our chapter here. So we're going to say an unknown distribution has a mean of 90 and a standard deviation of 15. A sample size 80 is drawn randomly from the population. So A says find the probability that the sum of the 80 values is more than 7,500. So let's write down what we know we already have. We know that mu sub x is 90 because that's what it tells us. It tells us that an unknown distribution has a mean of 90. The standard deviation of that collection is 15. And then our sample size is 80. Remember, this mean and standard deviation is not our mean and standard deviation of the summation, right? We're talking about the sum of the 80 values. So we have some work to do here. So if we go, and I'm just going to try to keep this in the screen here so we can kind of mimic this. This says that the summation of x is normally distributed, and that means our n, which in our case is 80, our mu sub x is 90. That's now our new mean. And then our standard deviation now is the square root of 80 times standard deviation of x, which is 15. I'm going to kind of move that out of the picture so we can work with our other values here. Hopefully I can fit them. So if I kind of follow this here, here's what I'm looking at now. Okay, I'm trying to mimic this. I'm trying to find what the mean of our summation is. So our mean of our summation, oops, I should probably write the mean, not just the summation. Our mean sub summation is n times our mean of x, which in our case is 80 times 90, and 80 times 90 will give you 7,200. Because when you first read this, right, when you first read this, think about what we've done in chapter 6 and so forth. When we first read this, we see that a mean is 90 and standard deviation is 15. And then all of a sudden, I'm asking you to test the sample, the data point, 7,500. That's way outside the scope of 3 standard deviations, which is where 99.7% of the data lies, right? So we need to make sure that we're like, hey, look, this would be a red flag. Why is this number so large? Maybe is it an extra zero? Even if it's an extra zero, that's still way large. So, but the key word is that it says sum. So we know that we have to multiply that mean and the sample size to get our mean of the summation. Now we're going to look at our standard deviation of the summation. And that's written by taking the square root of n and multiply it by the standard deviation of x. So we're going to take the square root of 80 and then multiply it by our standard deviation of x, which is 15. And when you actually put this in the calculator, I'm just going to give you a heads up. When you actually put the square root of 80 times 15, it does give you a really crappy number of 134.1640786. Okay. The problem with this is we are rounding if we use this. So I'm actually not going to put a value here. I'm not a fan of rounding unless we have to. Now, if somewhere in the question I say, what is the standard deviation? Then I'm asking you to round, and I will tell you to round to the nearest 10th or 100th. However, if I do not ask that question, or the question doesn't ask it, wherever you get the question from, then I would suggest to always leave it as an exact answer. And right now, this is not exact. That's rounded. If we say 134.16, that's rounded. We forget all this stuff. Okay? Or if we say it to the nearest 10th, we're 134.1. That's rounded. So I'm actually going to leave off all of this. Now I'm going to go to my z value, and I am going to lose at the top. I thought I could try to sneak this in there so we can follow it, but we're going to come down here. Maybe I'll just write it again. So I'm going to say z equals, oh, I got to switch to my pen here. Z equals the summation of x minus n times mu of x, and then our standard deviation, which is the square root of n times standard deviation of x. So actually, I probably should write this down just a little bit more. I might have jumped the gun because I wanted to identify all the pieces. Our summation of x is going to be 7,500 because that's our data point. That's what it's asking us to use right here. Okay, so now we can start substituting these values in. So 7,500. You can, and notice how 80 times 90 is a nice whole number, right? We didn't round this. That's why I can write 7,200. So I'm going to write 7,200 divided by the square root of 80 times 15. When you put this into your calculator, you get 2.24. And from there, now we need to go to our z table. So 2.24. So 2.2 is right here. And then 4 is right here. So here's the value we're looking for right there. 0.4875. Now exactly what do we do with this value though? Let's look at the visual. 7,200. We're at 7,500. But notice how it says find the probability that the sum of the 80 values is more than 7,500. So that means we're really looking for this. But this 0.4875 gives us right here. That's what it actually gives us. We don't want that. We want this out here. But if this whole thing from here over is 0.50, we're going to take this 0.50 and subtract this, and it'll leave us with that. So we're going to say that the probability that it's more than 7,500 is 0.5 minus 0.4875. 4875. That gives us 0.0125. This is the probability that the sum of the 80 values is more than 7,500. All right, so let's do one more with this problem. I ran out of room here on this page, so we're just going to have to go over to the next page. Oops. So let's say an add, let's find summation of x where, so let's find this data point where z is 1.5. I just want to kind of review with you how to find, when you have the z-score, how to find the data point. So if you recall, remember our z-scores on the left, so 1.5 equal to sub x minus 7,200, and then our square root of 80 times 15. So how you would actually do it to be exact, and this is to be exact, what you would actually do is you're multiplying both sides by that denominator, which is the square root of 80 times 15. All right, so now I have the square root of 80 times 15 times 1.5 equal to the summation of x minus 7,200. And then lastly, we add 7,200 to both sides. So what you really get is you get the square root of 80 times 15 times 1.5 times, or sorry, plus 7,200, which is here. Before I put this in the calculator, let's talk about, if you're looking for your data point, what are you actually even doing? Do I have to put it into this formula every time and then manipulate it? No. So let me show you. Really what this says, the square root of 80, if you recall, 80 was our sample size. So we have the square root of n, square root of our sample size. 15 was our standard deviation for x. The 1.5 was our z. And then we are adding, right? We have that point over there, which is our n. How do we get 7,200? Was n times mu sub x. That gives us our data point. So when I ask for a data point and it gives you your z, you can either do all this manipulation or you just plug the values into here and solve. It's the same thing. When you put into the calculator, I mean, it's exactly what you see right here. You put it into the calculator just like this. And when you do, we get 7401.25. That's our data point when our z-score is 1.5. All right, let's move to our last example here. Example 4 in our chapter says, in a recent study reported, I'm going to pause this and you can come back and it'll just be here. It might be a little bit faster. You can go ahead and pause the video to copy this down, and then I'm just going to start talking about it. So go ahead and pause now, write this down, and we'll go. So it says, in a recent study reported on October 29th, 2012 on the Flurry blog, the mean age of tablet users is 34. We've already known this. Suppose the standard deviation is 15 years and the sample size is 50, where the mean and standard deviation for the sum of the ages of tablet users. And what is the distribution? So remember, this says sum. Here's the key, sum. Remember that last example, I said, be careful what you're doing. All right, and I'll explain as we go. So first, we're going to say that we need to find the mean of the sum, which is n times mu sub x. So we have 50 times 34 equal to 1700. Great. Next, standard deviation of the sum is the square root of n times standard deviation of x, square root of 50 times 15. Now, on the last problem, I said stop here. Because if you recall, the last problem, it did not ask for this. It did not ask for standard deviation. It just says find the probability that this happens. But when it actually asks, go ahead and put that in your calculator and round. And we're going to round here to 2 decimal places to the nearest hundreds. So we're going to say 106.07. It says, what is the distribution? Well, think about it. We're talking about something with the central limit theorem, and the central limit theorem states by this with the central limit of the summations states as the sample size is large and gets larger and larger and larger, it's going to form a normal distribution. And that larger was 30 or more, right? So this sample size is 50, so this distribution will be normal for sums by the central limit theorem. So now B. B says, how about what's the probability that my value lies between 1500 and 1800? So let's find this probability. Let's graph this first. So our average here is 1700. 1500 is somewhere right in here. We're just putting values here, of course. We're just guessing where it would be. So right in here somewhere. So this here is going to be our summation of x sub 1, summation of x sub 2. So our first z value. I'm not going to write it all out, but we're first going to use the first data point, which is going to be 1500. We have the 1700 here, which is our mu here, our mean, which is 1700, divided by, and since it asked us for the standard deviation, we can just write 106.07. You do not need to write the square root of 50 times 15. 106.07. This gives us negative 1.89, and it should give us negative because it is to the left of the mean. So we're going to go to our z table, 1.89, 1.8, and then 0.09 is this last column here. So we're looking at this value right there, that 0.4706. That's the probability for right here. Now we need to find this. So here's our second z value. Here's our second data point, which is 1800 now, and then everything else stays the same, minus our average, which was 1700, divided by our standard deviation, which is 106.07. We put this into our calculator, and we get 0.94. Again, should be positive because we are to the right of the mean. Now we go to our z table, and we're looking for 0.94. So 0.9. And then the 0.04 is right here. And so here we are right there. 0.3264. So the question is now is, what do we do with these two probabilities? Well, remember, if we have this one is that, and this one is here, we want both of them. So we're going to add these values together. So the probability of the value falling between 1500 and 1800 is 0.4706 plus 0.3264. which is 0.7970. So this is where we have the probability between those two values. It is 0.7970, or a 79.7% chance that it's going to be in between those two. All right, one last part of this one before we call it quits. How about find the 80th percentile for the sum of the 50 ages? Well, let's kind of draw a little chart here. Our graph, our bell curve. If we're looking for the 80th percentile, we're out here. And this here is 0.50. So that means we're trying to look for in here, which would be 0.30. So we're going to go to our Z table and try to look for something as close as we can to 30%. So you can see we have 0.288 here, 0.29. Oh, we passed it. So it's between here. And we can totally tell that this is closer. So our Z value that gives us something really close to 0.30 is this 0.84. 0.84. Right, so because we have done all the hard work with finding the mean and the standard deviation, it seems a lot easier just to go through and say 0.84 equal to x minus 17. I should say the summation of x minus 1700 divided by 106.07. I'll show you how to do the math work of it. Multiply both sides by 106.07. I still leave it so I can get exact. Then you're going to add 1700 to both sides, right? So we have 106.07 times 0.84 plus 1700, the summation. Put all that to your calculator, and we get 1789.1. And I would suggest that you check too. If you think about where this value is, it's out here. Well, our mean was 1700. We need something a little bit further, which gives us something a little further, right? It's larger than the 1700. And there's your final answer. And that concludes our section 2.